Good day, viewers. Welcome to the Physics Mind. Today, we will continue from dimensional analysis from where we stopped in the last video. If you have not watched the last video, please go and check it. Okay, so dimensional analysis, and we've already looked at the different quantities and how we can obtain their respective dimensions. All right, today we'll be looking at how we can use dimensional analysis to check the dimensional correctness of an equation. Now, one of the uses of dimensional analysis is to what? To check the dimensional correctness of a given equation. And what do we mean by dimensional correctness? To check if an equation is dimensionally correct or it is not dimensionally correct. And in this video, we are going to learn how we can what? Check for the dimensional correctness of an equation. Now, how do we know if an equation is dimensionally correct or is not dimensionally correct? Now, you can know if an equation is dimensionally correct if each term of the equation is the same. That means that, for instance, we have these equations which we will be verifying if they are dimensionally correct or not. Now, if the dimension on this term is the same as the dimension here and is also the same as the dimension here, then the equation is dimensionally correct. Else, it is not what? Correct. All right. So we have some equations here which we shall verify or to check if they are dimensionally correct or not. So we have a question which says, use dimensional analysis to prove the correctness of the following formula. All right, now the first, we have V is equal to U plus 80, V squared is equal to U squared plus 2AS, S is equal to UT plus half 80, and S is equal to UT plus half 80 squared. Now, when you study your motion very well, you'll believe that these are actually what? Equations of motion. But one of them is not actually what? Correct. And we shall verify to know which of the equation is not actually what? Correct. So all the symbols here have their usual meaning. V here stands for the final velocity of the body. U stands for the initial velocity of the body. A here stands for the acceleration of the body. T here stands for the time taken. And S stands for the what? The distance. So let's verify to check if they are dimensionally correct or not. Now, the first equation we have, V is equal to U plus 80. Now, let's substitute their respective dimension and then see if it is going to be dimensionally correct or not. So, V here, we know it's the final velocity of the body. And the dimension of velocity, we know is already what? LT minus 1. So, be it an initial velocity or a final velocity, they are both velocity. So, they have the same dimension. So, final velocity is LT minus 1. U here stands for the initial velocity, and that is also LT minus 1 plus, now, acceleration. The dimension of acceleration we know is LT minus 2, then it's multiplying time, and the dimension of time is capital T. So we have LT minus 1 is equal to LT minus 1 plus LT. Now, from indices, this is the same thing as minus 2, then plus 1. So that will give us LT minus 1 is equal to LT minus 1 plus LT minus 2 plus 1. That will give us minus 1. So let us verify, is the equation dimensionally correct? LT minus 1 is equal to LT minus 1 plus LT minus 1. Yes, the equation is correct. So you conclude by saying, hence, the equation is dimensionally correct. All right, so let's verify for the second equation. Let's use this side of the board. Now, the second one, we have V squared is equal to U squared plus 2AS. So, V squared is equal to U squared plus 2as. All right, so v, we already know is the final velocity, and the dimension still remains the same as that of what? Velocity, but it is square, so we'll also square the dimension. So we have lt minus 1 square equals to u square, which is also initial velocity. We also square the dimension, which is lt minus 1 square plus 2. This 2 is a constant, so it doesn't actually have any effect. In fact, you will just solve it as if the constant don't actually what? Exist. So we have 2 into acceleration, which is lt minus 2 times our distance. The dimension of distance is what? L, the same as the dimension of what? Of length. Remember that both length, distance, displacement, radius, all have the same dimension. All right, so dimension of distance, which we say is what? Is L. Okay, so let's carry out the multiplication. So we have L, we'll open this bracket, we have L squared, t power minus 2 is equals, upon this, we have L squared, t power minus 2, and then plus 2 into L t, L times L, that will give us L squared, and then t power minus 2. So, giving us L squared, t power minus 2 is equal to L squared, t power minus 2, plus 2 into L squared, t power minus 2. So let's check, is it dimensionally correct? This is the same thing with this, and it's also the same thing with this. Remember, I told you that what? That the 2 or the constant there doesn't have any what? Effect. Your main concern is on the what? The quantities, not on the constant. So since this is the same thing with this, and it's also the same thing with this, so the equation is dimensionally correct. So we write that hence the equation is dimensionally correct. Okay, so that is that on the second question. So the third equation we have is S is equals ut plus half into 80. So let's verify if this equation is correct. So substituting their respective dimension, S, we said is a distance, and the dimension of distance is L, is equal to U is initial velocity, and the dimension is LT minus 1 times T, which is the time, and the dimension of time is capital T, plus 1 over 2 into A is the acceleration, and the dimension of acceleration is LT minus 2 times T is the time, and the dimension of time is capital T. All right, so let's expand the bracket. So we have L is equal to, multiply this, we have LT from indices, remember this power 1, so that will give us minus 1 plus 1. All right, plus 1 over 2 into LT from indices, remember this power 1, so that will give us minus 2 plus 1. So that will give us L is equals LT power minus 1 plus 1, that is a 0, plus 1 over 2 into LT power minus 2 plus 1, that is minus 1. All right, so we have L is equal to T power 0 is 1. Remember from indices, anything that is raised to the power of 0 is 1. So T power 0 is 1. That 1 times L, that will give us L plus 1 over 2 into LT power minus 1. All right, so let's check, is it dimensionally correct? Now we have L is equal to L plus 1 over 2 into LT power 1. So it is not dimensionally correct because there is T here, there's no T here, and there's also no T here. So the equation is not dimensionally correct. So you conclude by saying, hence, the equation is not dimensionally correct. So it is not correct. So let's try the last equation. So the last equation, we have S is equals UT plus half AT squared. S is equal to UT plus half AT squared. Now, when you look at this last equation, it's identical to the third equation. The only difference is that this T is having a square here, while this T does not have a square. So let's verify if this will be dimensionally correct or not. So all variables have their usual meaning. All right, so S is our distance. The dimension is L is equal to U, initial velocity, whose dimension is LT minus 1, times T, dimension of T is capital T, plus 1 over 2 into A, acceleration, dimension is LT minus 2, times T, which is the time, and is squared. So we have capital T squared. Okay, so we have L is equal to LT power. Remember, this T is raised to the power of 1. So we have T raised to the power of minus 1 plus 1. And then plus 1 over 2 into LT power minus 2 and 2. So that will give us minus 2 plus 2. That is from indices. Sorry, minus 2 plus 2. Okay, so we have L is equals LT power minus 1 plus 1, which is 0, plus 1 over 2 into LT power minus 2 plus 2, which is also 0. So we have L to be equals T power 0 is 1, because anything raised to the power of 0 is 1. So that 1 times L, we have L plus 1 over 2 into T power 0 is still what? 1. So that 1 times L, that will give us what? L. So we have L. So therefore we have L is equals L plus 1 over 2 into L. So is it dimensionally correct? Yes, it is dimensionally correct, because L here is equal to L here, and is also equal plus what? L here. Remember, the 1 over 2 here is a what? It's a constant. So you assume it doesn't even what? Exist. All right, so the equation is what? Dimensionally correct. So you write, hence, the equation is dimensionally correct. All right, please make sure you what? You like and subscribe to my channel for more videos like this, and stay tuned for more technical what? Questions, and especially WAEC and NICU questions from what? Dimensional analysis. Bye.